Hello friends, welcome to follow up. Let's have a look at problem 648, redundant connection. So before we start, let me first give you an overview of our plan. So our plan is to explain the UniFind method and the traversal method for problems of this type. So in the current video, we're going to present two formats of UniFind solutions. And in the follow-up video, we're going to present two formats of traversal method. So here, let's first look at the problem statement, and then we go to the coding. So in this problem, so we want to judge the redundant edge in a tree, right? So basically what we need to know is that tree is a connected graph with n nodes and n-1 edges, right? So in the current problem, we are given a graph that started as a tree with n nodes labeled from 1 to m. So with one additional edge added. So the added edge has two different vertices chosen from 1 to m, and was not an edge that already existed. So the graph is represented as an array edges of length n. Notice that this is very special. We have edge m. So the length of this edges list is m. So typically, for a tree, it will have n-1 edges. So if the length is n, so it means that it included an extra edge, right? So we want to return an edge that can be removed so that the resulting graph is a tree of n nodes. And if there are multiple answers, we're going to return the answer that occurs last in the input. So in the first example, so this is singly connected, right, for sure. So we can delete either 1, 2, or 1, 3, or 3, 2. But the last one is 2, 3. So we're going to delete this one or return this one. So in the second example, so we can delete see 1, 2, 2, 3, 3, 4, and 1, 4, right? But the last one is 1, 4, so we're going to delete 1, 4. So actually, it's also important to notice that in this problem, the number of nodes is bounded above by 1000. So this is not very large. So for example, if you have n square algorithm, so the Python interpreter or in your plain machine, it's doable, right? So, and also there are no repeated edges, and also the graph is connected. So this is just a set of comments for this problem. So in the current video, so we want to use this, address this problem by UniFind. So UniFind is also called disjoint set data structure, right? So typically there are two ways to implement that. So either we implement the UniFind as a class, or use it as a sort of data structure, or we can use them as of functions or methods like a union method, find method, and we implement within the function here, right? So here we are going to take the route, like we first implement the UniFind method as a class, and then we apply that to the current problem. So this is actually a longer route, but the reason we do this is to help you really digest the essence. So this is one point. Another point is that after we realize this longer route, we're going to implement a shorter version, so similar. So with that said, let's continue the coding part. As we mentioned, I'm going to implement a class called Disjoint Set Union. So let's first write the initializer, right? So here we are going to have self root. So let's use an empty dictionary. So self rec. So I'm going to use also empty dictionary. So what we want to implement is a find method. Let's see, given a root, we want to find its node, we want to find its root or its representation. So another one is union. So given two nodes, so we want to join them. So that's basically the thing. So here, the advantage of implementing this as a separate class is the following. So if we do not know a priori the number of nodes, so this will be much more convenient. If we finish implementing the find and the union method, this advantage will be more obvious. So now let's continue for this implementation. For sure, when we do this implementation for this class and for implement these two methods, we need to keep our use cases in mind. So here, now let's look at this one. So first, if I not in self root. So in this case, we are going to do self root I, so equals I. Self rec I equals 1. You can understand that the rec is the size of clusters in containing this I, right? So we need to return this I itself, because I is find the root or ancestor. So here, because it's just itself, we just added this information to the data structure. So we return itself. Otherwise, so what we want to do, so we have let's set result equals self root I, right? Now we use a while loop. While result does not equal to self root result. Then we just retrieve up along this chain. Basically, we want to set result equals self root result. And then finally, we just need to return the result. But for this problem, I want to use something called path compression. So we don't need to use this one in the current problem, but it's good to know. Root result. Basically, we apply this self root once more to this. So this actually plays the role of path compression. So this is just one way to implement path compression. So in this problem, it's not necessary, but it's good to have here because it just added one more line of code. So then this is the find method. Now let's look at the union method. So before the union method, I also want to implement another method called sim root. So given two nodes, I want to see if they are belonging to the sim cluster. So this actually is very simple. We just need to return self find I. So this is the root of this node. So whether it's equal to self find G, right? So now let's look at the union method. So first, we want to see the root I and the root G. So it's self find I, self find G, right? So if root I equals root G, we do nothing, right? If they are not equal, so we just need to set one to be the ancestor of the other. So basically you can do this, see self root of root G equals root I. And then in this case also I want to update the rec. Self root I is incremented by self rec of root G. So you can imagine that we put all the nodes in root in the cluster including G to the cluster including I. So for this problem, we don't need to use this. This is so-called union by rec. But let's implement that just to give you more information. So here we check the rec. Self rec root I is greater than or equal to self rec of root G. If this is the case, means that the cluster containing root I is larger. So we set the root of root G to be root I, and then we increment this. Otherwise, so we do the same thing, but in the reverse direction. Let's copy this part. And then we are going to set the root of root I to be root G. And then we increment the size of root G by that of root I. So this is the union method, right? So here we actually implement union by rec, right? And here we implement this find is the find with path compression. So for this problem, due to the problem size, because n is bounded above by 1000, so we don't need actually to use compression and union by rec. But for the later applications you might have, let's add these two features. So now let's look at the problem logic here. So here, let's initialize this DSU object, right? And then we're going to iterate for AB in edges. So what we want to do is that we check if they have the same root. In other words, if they are actually within the same cluster, it means this is a redundant edge. So we are going to delete that. So also, if you want to incorporate this information, if there are multiple answers, we return the last one. So let's use an aux to brute forcefully get this information. Actually, for this problem, due to the setting, once we meet a same root edge, we can directly return. So now let's see. If not, DSU same root AB, then we just do union. So DSU union AB. So otherwise, what we do, we aux append the current edge. Let's see, AB. Because we want to return the last one, so we just need to return aux -1. So this is the problem logic. So once we have the DSU data structure, and then just use it, then we can directly get a solution to this problem. So before we make any comments, let's first do a test. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the generic cases. So as we mentioned, first I want to make a comment for this, this part. So here we can comment this out, and then else we just need to return this AB. And also we don't need this line. So this is due to the problem assumption, right? It has one extra edge ended. So let's do a test. It passed a special case. Now let's look at the generic case. Yeah, it passes all the generic cases. So this is the one way of doing a union find. So for this problem, it looks a little bit longer. So now let's copy this part, copy the function signature here, class. I'm going to implement the union find method within this solution method. So I'm going to change this one to be solution v1. Now let's ignore the previous one and do this. The reason we can implement within this function is the fact that the length of this edges list is nothing but the number of nodes. So in other words, we a priori know how many nodes we are going to have, right? So in this case, we're going to directly define a root as nothing but I for I in range. So notice that the indexing is from 1 to n. So here we're going to write 1 n plus 1. And then the rec, so we don't need actually the rec, because here we use the union by rec, and here we use path compression. So here I want to write a shorter version. So let's ignore this rec part. So in other words, here we just implement the vanilla find and the union method. Let's first look at the find method. The find. So here I pass a node. We want to find its root. So you can do as here, right? That's this main part. But you use a while loop. But here let's use recursion. So here I'm going to return I if root I equals I. Otherwise, I'm going to return find root I. So in other words, we are using recursion here. So then let's define a union method. So ig, right? So here first let's see root I, root j is find I, find j, right? So if root I does not equal to root j, what we want to do is to set, right, say root of root J equals root I. That's it, right? So also let's define another method, same root. So given ij, so we just need to return find I equals find J, right? So notice that this method here we do like a union and the find. So essentially we can write one layers. However, these two methods are just the vanilla find and union method. If we have a problem size much larger, let's say 10 to the power 6, so it will be significantly slower than the function using path compression and union barrage. So now with that said, let's look at the problem logic, right? So for the problem logic, it will be the same as above. So you can use an arg list or something like this, or you can directly do return. So here, let's see, for edge, so in edges, so let's call ij equals the edge, right? Or you can just put ij in the for loop. And then what we want to do is check if there are same root, ij. If so, we just need to return this edge. Otherwise, what we do, we just do union, right? Union ij. And due to the way of this problem, so this will return the correct answer. So now let's do a test. Yeah, it passes one example. So now let's look at its generic case. Yeah, it passes all the generic cases. So now if you want to make it very safe, so you can do as in previous, you can have this one, right? So if they have the same root, you are going to do append, right? Aux append this edge. And later what you do is to return aux -1, the last one. So now let's do a test. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases. So up to now, we finished the two versions of union find. So let me give you a quick summary. So here we implemented two formats of union find. So one is as a independent data structure or class, and then we instantiate it in the problem logic, then do the problem. The second format is that we implement the find and the union method within this solution method, right? And then because we already know the number of nodes involved, so we can do this directly. And also we explain some details for the return. So with that said, I guess that's about it for the current video. So in a follow-up video, we're going to explain another route of solutions to this problem based on traversal. You are welcome to follow up. Thank you.